Hello everybody and welcome to another episode of Dispar's Lab. Today we're going to do another kinetic energy experiment. It's going to be a dropping experiment. So as you can see right here I have a steel bar and there's the ruler, and this is going to be the mass that I'm going to be dropping, which is a big wooden ball with a hole in the middle. Okay, and the diameter of the hole is big enough so that it can easily slide over the bar with barely any friction. And then we have the target, which is a pincher. I'm sorry if there's too much noise outside. And so this is a pincher, which grabs onto the bar with a constant force. So there's a constant friction being applied to the steel bar. And so as I drop the ball from a certain height, there's going to be displacement. The pincher is going to displace. It's going to drop a certain amount. And so the first dropping height is going to be 10 centimeters. I don't know if you can see this, but the surface of this surface is aligned with the 20 centimeter mark. So here is 20 centimeters, you can see that. Okay, and now this one is aligned with the 20 centimeter mark. Okay, and then I'm going to raise the ball. Oh yeah, I forgot to mention, this is a little piece of cloth to dampen the sound a bit. Because there is sound and it is also a form of energy. You want to reduce the amount of sound escaping because that's going to be a little bit of a loss of energy. So I'm going to raise the ball to 30 centimeters. You can see the bottom of the ball is aligned with 30 centimeters. So the dropping height is now 10 centimeters. I'm going to release it. Okay. And we can see, hopefully, yeah, you can see that it has now reached a height of 90.5. It dropped a half centimeter, so the displacement is a half centimeter. So this is 19, and this line is the 19.5 line. So it has dropped around half a centimeter. So I will do a couple of trials, and then I will raise the ball to a dropping height of 20 centimeters, and then raise the ball to a dropping height of 30 centimeters and to 40 centimeters. The point of this experiment is to test out this formula. Energy equals mass times gravitational acceleration times the distance. So when the distance is doubled, we should get twice the amount of impact, twice the amount of energy, twice the amount of displacement. When the distance is 3 times as much, we should have 3 times as much energy. When it's 4 times as much, 4 times as much energy. On the other hand, there are certain people who believe that this is not true and that energy equals mass times gravitational acceleration times time. That it all depends on how long it falls in gravity. So, for example, when we drop it from 4 times as high, that means it's going to go twice as fast. It will spend twice as long in the air, twice as long into gravity. And so according to these people, when it's twice as long, so 4 times as high, it's going to be only twice as much energy. So according to conventional science, 4 times as high should give us 4 times the energy. But if it's time dependent, then it's 4 times as high means twice as long, so only twice as much energy. So let's find out whether or not, or which of both is correct. Okay, 10 centimeters, trial 2. So it's still a line of 20 centimeters. And once again, the displacement is half a centimeter. 10 centimeters, trial 3. The displacement is 0.5 centimeters. 10 centimeters, trial 4. Once again, the displacement is 0.5 centimeters. 10 centimeters, trial 5. Uh, 0.6 centimeters of displacement. 10 centimeters, trial 6. 0.6 centimeters. 20 centimeters, trial 2. Displacement is 1.2 centimeters. Okay, 20 centimeters, trial 3. Displacement is 1.2 centimeters. 20 centimeters, trial 4. And again, around 1.1 centimeters of displacement. Okay, dropping height 30 centimeters, trial 1. And displacement is around 1.7 centimeters. Alright, 30 centimeters, trial 2. Displacement is around 1.7 or 1.7 I think. 30 centimeters, trial 3. Once again, this is a 1.6 centimeters, I believe. Yeah. 30 centimeters, trial 4. And this time we have a 1.5 centimeters of displacement. Okay, dropping height 40 centimeters, trial 1. Displacement is 2.2 centimeters. 40 centimeters, trial 2. Displacement is 2.3 centimeters. 40 centimeters, trial 3. Displacement is 2.2 centimeters. Okay, 40 centimeters, trial 4. And displacement is 2.1 centimeter. Yep. Okay, dropping height 50 centimeters, trial 1. Displacement, is 2.7 or 2.8. I think it's 2.7. Yeah, around 2.7, 2.8. 50 centimeters, trial 2. Two 2.7. 50 centimeters, trial 3. That's 2.6, yeah. 50 centimeters, trial 4. .5-ish, yeah. Dropping height 60 centimeters, trial 1. I'm sorry, there we go. Alright. Looks like 2.5 centimeters of displacement. Hold on, 3.5 actually. Yeah, 3.5. 60 centimeters, trial 2. That's 3.2 centimeters of displacement. 60 centimeters, trial 3. And 3.2 or 3.3 centimeters of displacement. 60 centimeters, trial 4. .2 centimeters of displacement. Alright, so these are the results. Here we have the displacements for the dropping height of 10 centimeters. So we had between 0.5 centimeters, and then 2 trials I had 0.6 centimeters. Then dropped from 20 centimeters, I had between 1.1 and 1.2. So the expectation is times 2, so 0.5 times 2, so between 1 centimeter and 1.2 centimeter. So that's very close in that range, between 1 and 1.2 centimeters for the twice the height. Then for 3 times the height, 30 centimeters. So the expectations are this times 3. So 0.5 times 3 is 1.5, and 0.6 is times 3 is 1.8. So between 1.5 and 1.8 are the expectations, and the results are very close within that range, between 1.5 and 1.7. Then for 4 times the height, the expectations are, so times 4, which is 2 centimeters, and then 0.6 times 4 is 2.4. So between 2 and 2.4. And my results are 2.1, 2.2, 2.3, 2.2. So once again, very close within that range. Then for 5 times the height, so this times 5, so 0.5 times 5 is 2.5, 0.6 times 5 is 3, so between 2.5 and 3 centimeters, I got 2.5, and between 2.5 and 2.7, so once again, very close within that range, very close within the expectations. And then for 6 times the height, so this times 6, 0.5 times 6 is 3, and 0.6 times 6 is 3.6, so between 3 and 3.6 centimeters, and I got between 3.2 and 3.5. So once again, all the results are within the expectations. So as you can see, it is correct that energy equals mass times g times the height, and so which means that physics works. Physics works, people. Distance, or the height, is crucial. It's a height dependent thing. The energy depends upon the height, not the amount of time. m.g.h.